Welcome, everybody. This is the Rotary E-Club of Silicon Valley, and every week we bring you the stories of people who are making life better for others around the world, locally, globally, and digitally. We're part of a group of about 1.2 something million Rotarians and Rotaractors in 36,000 clubs around the world. This is a group of people who live by the motto service above self. Rotary is an organization devoted to improving communities in all sorts of ways. And for us in the Rotary E-Club of Silicon Valley, an online and asynchronous club, a lot of that comes down to finding really amazing and inspiring stories about breakthroughs in all sorts of ways to share with our friends all over the planet. To that end, we have today a professor from the University of Massachusetts Amherst, Trisha Andrew, who is I think unconventional is the right word. It comes up a couple of times in the bio, and for good reason. She does all sorts of really interesting work, and at a time when we are dealing with rising temperatures in all sorts of places, the kinds of work that her team is doing will be, I think, very intriguing for you. So, if you want to take a look at the longer bio, you certainly may. You can pause this, scroll down a little bit on our YouTube page, or scroll up a bit on our Rotary page, or go back to the podcast page. Wherever you are finding us, feel free to do that. But I will get right to it. And Trisha, we are so excited to have you with us. I hand the mic over to you.
Thank you so much, Rushton. Thank you for the invitation and the opportunity to speak to your club. And so I'll talk a little bit today. I'll try to keep my professorial nature in check and be done in 10 minutes, but I'm going to talk to you about our lab's recent work in trying to help people maintain what's called thermal homeostasis in a changing climate, and specifically for maintaining or reducing heat stress in a warming climate that I'll focus on today. So the general idea, or actually before I start, this is why I always have my slides in this order. So I always thank my team before I get into it. So this is a snapshot of my lab through the years over the past, let's see, the oldest picture is 8 years old now. And these are all the people that have worked on various aspects of textiles and garments and finishes and electronics in my lab since I started as a professor. The work that I'm going to talk about today is primarily done by Evan Padamia and Megan Yee, who are in the right middle part of this t-shirt diagram. And this also gives you an idea of some of the other things that my lab works on. We generally think about how to use coatings to make functional everything, even plants actually. And on the left are all the people that have supported us through the years. A lot of work and financial support from the federal government, and also some private companies that are interested in a lot of the things that we do in my lab. All right. So the general background here is surely known to most people, but just to be specific about some numbers, the Earth is warming. And if we don't take action, the projections for that warming, for the temperature across the world, are shown in this middle picture here from the references for the paper is provided on the right. This is a projected maximum mean monthly temperature, again, for the globe in between the years 2091 and 2100. So this is not tomorrow or right now, but in the future, assuming that we don't actually change our emissions or if we don't change our behaviors that we have been kind of performing for the past 50 years. And this temperature is actually a weird number. It's called the wet bulb temperature, or WBGT, global temperature. And what that actually is not just a measure of the temperature, but it's a combination of the temperature and humidity. And this number is actually useful because it's kind of human-centric. And the humidity is important for humans and understanding when heat stress actually is going to start afflicting humans. The graph on the very left of the slide is the results of studies from the PSU Heat Project, where physiologists basically studied, I think, about 500 people considered in the healthy range to look at when physiological heat stress, so this is not someone feeling hot, but the physiological condition of heat stress, when heat stress had an onset in a healthy population between 18 to 35 years old at different temperature and humidity conditions. And so the bars are showing you where that really onset is. Oftentimes, what is found in medical textbooks or even on Wikipedia is usually the human threshold for livability is 35 degrees Celsius. And what this paper and this project really showed is that that kind of is not exactly true. At very, very dry temperatures and hot temperatures, so in a desert, for instance, physiological heat stress in healthy adults can have an onset as early as 24 degrees Celsius, not just 35. That onset is closer to 32 when there is a higher level of humidity. But the point here is that heat stress can actually start affecting humans and human health and actually leading to death much earlier than we thought that was going to happen. And translating both of those bar graphs in this picture in the middle to the right, this is a map, a heat stress map, basically in the year 2091 and to 2100, the number of days that is going to cause basically death because of heat stress across the world. And you can see, obviously, countries, nations around the equator, are going to have a lot of heat deaths because of the warming climate. So obviously we need to find ways to maintain our body temperature. In other words, cool our bodies when we go outside, or even if we're existing in built environments without additive heat space cooling. So let's talk about how heating happens very globally. There's three general mechanisms. One's radiative heating or optical heating. There's conductive heating and convective heating. When we get warm, the kind of our intrinsic nature is to shed clothing or wear gauzy, breathable, lightweight fabrics. And the only thing that addresses is that convective cooling part, where we are enabling or preventing the movement of air and evaporation from our sweat. But the problem from all of those graphs in the past, in the last slide, is really coming from that one kind of heating that involves the sun, and it's radiative heating. So just because we shed layers of clothing, we're not going to actually prevent radiative heating. And we all really know this in our kind of body. If you go out in the sun, even if you're wearing a bathing suit, you're going to get hot. That's what this is telling you. And the problem is going to get even worse in urban environments, because when you think about this heating as actually an optical effect and it's not just convection or conduction, then when you are actually in an urban environment, buildings, asphalt, concrete, they actually all are highly reflective surfaces. And so you end up being in basically a hall of mirrors, where the mirrors are buildings and the pavement, and the light that they're reflecting is from the sun. And so the relative temperature, again, if you just look at the optical profile in urban environments or built environments, even suburban environments, is going to be higher than that in an open grassy field or the forest or somewhere out in nature, where there are just open ground and water that is doing the absorption instead of reflecting it back at humans. And I'm going to have you keep this picture on the very right in your mind as we talk about kind of testing further down, where you are basically that those red arrows are showing how buildings can act as sort of a hall of mirrors to reflect the sun's light. And I'm going to call that a complicated optical environment. So keep that picture in your head when I use that phrase later in a few minutes. So in nature, people have basically observed that natural beings have found ways to adapt to these highly testing environments. The classic example, if you look up radiative cooling in Wikipedia, it literally says the Saharan silver ant has been inspiring researchers to do radiative cooling for more than a decade, and that happens to be true. So this is a classic example of something found in nature, of an animal found in nature that has adapted to a very punishing environment. So as the name suggests, this is an ant, species of ant that is found, that is native to the Sahara Desert. And I'm going to call it silver in quotations. It's actually not a silver ant. It is a red ant, as you can see from this picture, but it has this silver sheen. In 2015, a group of biologists from a multinational university group, including the University of Washington, found that the reason that these ants are silver is actually the hairs on their body. The ant itself is just like a red ant that you could find in North America, but the Saharan silver ant has these very special hairs that are not found in its North American cousins that give it its silver shine. The pictures on the right actually show scanning electron microscope images of these Saharan silver ant hairs. And focus on the middle picture in particular. That is this one right here. This is showing you a zoomed in picture, cross-sectional picture actually, of each of the hairs. And the interesting thing about this is that these hairs are triangular. If you know anything about nature, sharp angles don't really survive. It's much easier to just have round hairs. In fact, our hairs are just all round and cylindrical. These ants' hairs are triangular. And this, international group of researchers who included some computational physicists actually ran some computations on the reflective properties of an individual hair. And they found that the triangle was really important because it acted as a refraction point for infrared light. And so through evolution, these ants actually have developed these very interesting triangular shaped hairs that reflect visible and infrared light from the sun. But it actually is even more complicated than that. If you look on the image on the rightmost part here, the hair is not actually uniform on all faces. So this top part over here, this is showing you the triangular hair at a more zoomed out level. And one surface, or two of them, actually have sort of roughness along them. And the other one down here is actually smooth. And this hair, the smooth part of this hair is basically the thing that's going to be exposed on the underbelly of the ant. And then these rougher surfaces, all in a triangle, but the two rougher surfaces are facing the sun. And what ends up happening is that the two surfaces that are comparatively rougher that face the sun are highly reflective in the visible region of the electromagnetic spectrum, so roughly around 0.2 micrometers to about 2 micrometers, okay? Or 200 nanometers to 2000 nanometers, whatever unit of reference is your favorite. Again, visible where we see light, Roy G. Biv, that is between 400 to 800 nanometers or 0.4 to 0.8 microns, all right? So this is across the visible and the infrared region. The rougher surface of the hairs, which faces the sun, they are very reflective. They actually reflect that light. They reject that light from actually entering the ant's body. And then on the bottom smoother surface, if you look at the reflectivity of those hairs at much longer wavelengths, so going past 2 micrometers, from 2 to 16 micrometers now, or 2000 to 16,000 nanometers, in the mid-infrared region, those hairs are actually not reflective. They are called emissive, or basically transparent to that region of light. So what's happening here is that the hairy surface, the rough surface that is facing the sun, rejects sunlight from actually hitting the ant's body. And so it actually does not feel the sunlight, even though it is out in the desert. The ant's body is not heated up by the sunlight. The smoother surface of the hair on the bottom, on the ground, allows the natural heat from the ground and any heat that actually the ant's body produces to be ejected out and transferred to the ground. And so there's this dual action, one reflective, one opaque or transmissive, across different regions of the spectrum. And that allows the ant to basically maintain a cool body temperature, normal working body temperature, just like the North American ant, even though it's out in the desert. There are some more examples here, more about the, again, spectrally selective, that's what it's called, nature of various organisms. The next common organism that everyone looks at is basically shellfish. So this is a nice abalone shell. A lot of physicists look at this for its structural coloration, the pretty iridescence, and how to make that happen in artificial systems. What I really care about, or what we're going to be talking about specifically, is that all of the shellfish, abalone included, but also common garden variety oysters, have all of their shells are made of various forms of calcium carbonate. And interestingly enough, calcium carbonate is highly reflective in the visible and infrared region and opaque or transmissive in the mid-infrared region, just like the hairs of the ant. So you don't necessarily need to have a triangular fiber like the hair of the ant. You could also use materials like calcium carbonate to fulfill the same purpose of reflecting some regions of sunlight and being transparent and allowing for ejection of heat in other regions of the electromagnetic spectrum. And you can see some of these adaptations among humans. Adaptations is not quite the right word, but across history, across different parts of the world, especially in the American South, in the Mediterranean, and in southern India, a very common procedure is called lime washing, which basically has calcium carbonate, either synthetic calcium carbonate, or in Greece and southern India, for instance, it's literally ground up shellfish or sea organisms. The buildings are just painted with this calcium carbonate. And this historical practice, even if it wasn't necessarily labeled as being for radiative cooling, does help cool buildings. This calcium carbonate paint actually rejects a lot of sunlight, the visible and IR parts of the sunlight, and allows heat from the inside of the building to still be ejected out without absorbing that. So the general idea, as you can tell, is for personal cooling, for allowing people to manage a rising climate, is to make clothing that mimics these various natural adaptations and or this process of lime washing. And just to summarize here, the idea is that you have some kind of garment, which everyone needs clothing, obviously. Ideally, there is something about this garment that allows you to reject some parts, some wavelengths of the incident sunlight, while also being transparent in a different region, just called the atmospheric window, so that your own body heat can actually exit your clothing. Right. So that's the big key here for on-body versus other building kind of cooling, is that last bit, the infrared, or 8 to 13 microns, as the slide says. You need to be able to have not only a reflective coating, but something that still allows your natural body heat, because we get hot too, not even if we're in the dark, to be radiated out. And this basically limits the amount of materials, the amount of strategies that you could use. For instance, a really common idea, if I just talk about the reflectivity of something, is to say, well, can't I just use those metallized blankets that people have to hold heat in? And the answer is you can't, because while it is going to reject the sunlight, it's also going to hold your own body heat in. So guess what? You're still going to get hot and sweaty and have heat stress, even if you just have a metallized blanket. So this is the materials challenge. How do you have something that's ideally 100% reflective between 0.2 to 2 microns, and something that's ideally fully transparent or fully emissive between 8 to 13 microns? That is a very large region of the electromagnetic spectrum for material scientists, but also that is a complete kind of orthogonal responsibility, one reflective, one fully transmissive. And so what my lab did has been working on, or we showed, is a multi-layered coating. And in the interest of time that I've already sped through, I'll talk about the fabrication process if someone is really interested, if there's a question. But this is the overall summary here. The cartoon is showing kind of breaking down the multiple layers. And we had to actually make this seemingly complicated structure with 4 layers, green, blue in the schematic. The green is a barium sulfate crystal. The blue is calcium carbonate. I didn't talk about barium sulfate before. That's something that we came up with. There are a couple of hackers on YouTube that have also used barium sulfate to cool down their houses and other hobby projects. And barium sulfate is actually used for medical imaging. Also happens to be another material that is highly reflective in the visible, but also fully emissive in the mid-IR region. And what we showed is that just one of them, just painting on something like this, or in other words, grabbing the lime wash that you can get buy for your houses and slapping it on your clothing, doesn't actually work because your body is three-dimensional. And then we're going to be in a complex optical environment in an urban built city. And that means that we are being impinged upon with light at different angles. And that simple lime wash doesn't work. It works great for a flat planar surface like a building, but not your body. And so what we had to do was treat this like it was a laser system and actually make a dielectric mirror. And a dielectric mirror basically has a system of multiple interfaces. And basically that's why we had 4 layers. And at each of that layer, you're going to have an increased number of reflection because of Snell's law. And so overall, this coating, as light is penetrating through, each layer reflects more and more light as light passes through the top down to the fiber underneath. And overall, this allows us to basically have angled independent reflectivity greater than 90% across the visible and infrared region, while also using fabrics that are naturally intrinsically transmissive or emissive in the mid-infrared region in the atmospheric window shown here. Sorry. So this is the high emissivity, or basically telling you that it's very transmissive. And then here it is highly reflective on the visible and the infrared. These are pictures. So this is we could do this on any fabric, any commodity fabric, any garment that you give me. This is a piece of polyester poplin, which is commonly found in sunsetter fabric and also at a lighter weight with a smaller yarn in outdoor clothing and sun protective clothing. So this is the natural fabric, and then this is after coating. You could see small crystals or reflective parts over here. That is the coating, but otherwise the fabric does not feel any different. It does not weigh any different. It does not have any different breathability or any other kind of perceptible features from the coating itself. As you could tell, because there's a lot of inorganic particles, it takes on a matte sheen. That's the only real perceptible difference. But other than that, it doesn't change much. So here's our testing setup because we actually have to understand if this works or not. And so my students built a little test setup over here with all of our wires. There's a solar power meter over here, the humidity sensor, wind sensor, etc. There's our reference sample, which is usually just the uncoated piece of fabric that we're testing, and then we could test 3 at the same time. And the key here is that we use a synthetic skin replacement. That's what we are calling the absorber paper, that allows us to actually absorb any sunlight that penetrates through our top layer of fabric or coated fabric. And we have a thermocouple that is testing the temperature of that kind of skin simulant out in different conditions. And as you can see here, as our coated sample, we can actually have a much colder temperature. The synthetic skin, or the skin equivalent, is feeling a much colder temperature than the skin that is just covered with a regular commodity fabric. It can be up to 8 degrees Celsius colder. This is an open field condition, as that picture kind of hints at. But the real test for us was in this complex optical environment. And so we tried out a couple of different scenarios. There is a concrete alleyway between glass buildings. There's a lot of nice reflective glass surfaces over here, an asphalt parking lot in the summertime at afternoon time, where there's a lot of reflective surfaces from the car, from the windshields, and also the asphalt. And then an open concrete pavilion that is surrounded on all 4 sides with skyscrapers. And in our most challenging environment, which is a parking lot, parking lots are death. Parking lots have resulted in over 500 deaths in the Sunbelt states of the United States in the past 3 years alone. Parking lots can be up to 5 degrees Celsius hotter than the ambient environment. And again, a wet bulb temperature increase, including a humidity here of 2 degrees Celsius, could mean heat stress. And so we were able to show with our coated fabrics, basically, that the simulated skin felt a temperature difference of 3.4 degrees, a maximum of 3.4 degrees lower than the ambient temperature without the coating. So that is literally the difference between life and death in a parking lot for cyclists and pedestrians. And we could go higher in more open environments, but the parking lot was our most challenging one because we have a lot of radiant heat from very low angle sources coming from, again, parked cars, but also the asphalt on the ground. So that's it. Oh, and this withstands washes. It really doesn't change. It has to do with our fabrication process, which is creating a covalent bond between all these crystals and the fabric and the polymer underneath. And so you could throw this in the wash and you could rub the heck out of it and it's not really going to go anywhere. And the performance is not going to change. For this study, we've done only about 35 washes, but my lab has worked extensively in coatings like this in the past, and our coatings have survived greater than 50 washes across different applications to date. And I think that is it. I'll end here with our little table of contents graphic for this work. And I'm happy to take questions from anyone who's interested.
Fantastic, Trisha. Man, we got a ton of questions here. I think what we'll do is go ahead and stop sharing. I'll quickly introduce the folks that we've got in the group. There are three of us from the Rotary E Club of Silicon Valley. Wave when I call your name. In Walnut Creek, Shag Shagrin, our club's paella master. In Houston, oh, nicely done, sir. In Houston, Texas, with sidekick Gus somewhere close by, is Rory Olson, Gus the cat, who likes certain kinds of music. My name's Rushton Hurley. I'm in San Jose, California. Trisha, let's get started with this is really cool science. When we think about these kinds of coatings on fabrics, how much of the ability to handle heat coming from the body is specific to the kind of heat that comes from the body, as opposed to, say, creating a blanket that has this kind of coating on it in order to put it over something that you're hoping will just be less hot for one reason or another. Maybe an outside piece of furniture, or it could be anything, but maybe just a non-living object. Is that something that can be done?
That absolutely can be done. I mean, in terms of developing the materials and the coating, I guess there really is no difference. That region where everything is sort of emitting heat, if you will, black body radiation, that's roughly that 8 to 13 micron window. Even things that we feel as heat basically is in that region. Maybe goes out to 15 microns, but that's really sort of it. So that those numbers kind of determining where you need to be reflective and where you need to be emissive are roughly the same for inanimate objects, for humans, for animals, etc.
So yeah, I mean, I can imagine this being something that keeps a pet alive.
Absolutely.
If you have the right kind of clothing. I was intrigued that you pointed to the Saharan silver ant, right? I mean, like that. I've been curious to find biomimicry examples for programs for a long time. At what point along the way for you was there an aha in terms of pursuing this research, pursuing the kinds of materials development that your lab is doing? What was there a moment that's like that was when I was like, I'm spending time on this?
Yeah. Um, yes, and it had really nothing to do with animals. It was the pandemic. It was really my students. So we started this effort in what I call optical thermoregulations, very jargony term for this, but we started this actually back when we were shut down. So UMass campus was, along with a lot of other places, was shut down, and we had very strict operating rules in 2021. And a lot of my students, including myself, took up gardening. And I had two students in particular who kind of really got into it and were looking at very exotic plants. And they were somehow stumbled upon a Arctic geranium, or a geranium that grows at very, very low latitudes, I think. And they started looking at these papers, thinking about the influence of the melanin concentration on the surface and how different plants have adapted to survive in very cold temperatures. And that led us actually to our first work in this, which is to make a polar bear fabric, where it allowed humans to actually gain or kind of harvest warmth from the sunlight in Arctic environments. And so you could go out in just a t-shirt, basically just something as thick as this inner layer in the Arctic. In Fairbanks, Alaska, we actually had this tested in the sunlight and feel as if it was, you know, Seattle, Washington, basically. And when that student was doing that work, he had a colleague sitting next to him who obviously asked the reverse question: can we keep people cool in very hot temperatures? And that kind of exploration led him to the silver ant paper that I highlighted in my talk. So it was, you know, really a lot of boredom from the pandemic, but the biomimicry part, you know, is very normal for scientists, especially material scientists, where it's always not necessarily driven by recognition of nature, but it's more of an acknowledgement of, you know, if someone has done this well, we should follow that as a strategy to basically design our own things.
Well, speaking of that, let's talk about design in terms of the fabrication process. So that was something that you teased us with along the way, and I'd love to hear more about how that became a part of making this research go from, hey, theoretically this is amazing, to we've got this, we're testing it now.
So as I said in the story of, you know, our first work was actually about making a polar bear fabric, as we called it, and, you know, for keeping people warm. And the reason for that, we started working on both kind of ideas at the same time, but this cooling bit actually took us a long time, 2 more years, to really feel like we made a change. And the short answer was, again, as I said before, you can't just take sort of lime wash paint or some equivalent of it that you make for fabrics, slap it on, and actually see a difference. And so the very beginning of this project for the student was a lot of, it didn't work as much as I wanted. In our testing setup, he made a lot of, and there are a lot of papers that talk about crushed up calcium carbonate or shellfish, or, you know, abalone shells, or all this other kind of stuff. And that, you know, he tried to make various versions of that. And even from the YouTube video that I mentioned with barium sulfate, try to make a fabric paint version. And when he tested those fabrics, they did not really give us sub-ambient cooling. They were fine, maybe. They didn't heat up as uncoated fabrics, maybe, but they didn't really do a great job. And it took us a while to really understand the complexity of that optical environment and realize that we had to treat this like a laser physics problem, and we had to make a dielectric mirror. And no one makes a dielectric mirror or laser optics on fabrics, because fabrics are a very complex surface. There's the fiber that goes into the thread or into a yarn, and that yarn is woven into a structure, or knitted into a structure. And then that structure is made into a garment that has its own kind of three-dimensional form. And so that is multiple length scales. That is down to 100 nanometer length scale on the fiber level, all the way to a millimeter length scale on the garment level. And laser optics need to have fidelity at the 100 nanometer level. And so this is really why you don't find fabric-based lasers or mirrors out there. And we actually have a technique that we developed a long time ago in my lab called chemical vapor deposition that allows us to grow polymers from any surface, from the molecular scale up to a polymer scale, in real time. And so what we realized is that we actually could make a dielectric mirror if we chose the right material. So our first job was, okay, what do I want to use? Let's We ran some computations, ended up with calcium carbonate, barium sulfate because they were cheap, they're biocompatible. They are sometimes even ingested by people if they have heartburn or if they need to get a medical test. And then we kind of had to understand how thick these layers need to be. And then we had to basically develop new chemistry for this chemical vapor deposition process to deposit these crystals of calcium carbonate and barium sulfate and make sure that they don't intermix so that they still have this sort of nice delineation. This is a barium sulfate layer, and then here's the calcium carbonate layer. So we developed three kinds of chemistries. One was an interleaving polymer layer. It's kind of like a saran wrap, but that saran wrap also grabs onto the actual metal salt. And then we developed two other kinds of chemistries to vapor deposit calcium carbonate, starting from ions, actually. And then we followed that up with more saran wrap. So that's kind of like wrapped up in its own layer, like a little Swiss roll. And then we do the barium sulfate. That was the third chemistry we developed. And then more polymer, calcium carbonate, barium sulfate. And so all of that, starting with computation, what size do we need to make? We need to develop new chemistry for this process that we've been doing a long time in my lab. And then we actually have to make these 4-layer structures. That took us an extra 3 years. And so polar bears came first, and then artificial nacre basically came 3 years later.
Well, this is the kind of stuff that inspires young scientists for sure, which I'm guessing is not unrelated to the kinds of grant materials that, well, I say grant, that you note among your supporters, the Packard Foundation, 3M, the National Science Foundation. Uh, is it the unconventional nature of these questions that got them excited about supporting the kinds of work that your lab does?
I think so. I mean, the thing about unconventional questions is that you learn more than one thing. I've always been lucky to work with really creative people, and so we happen to always find or make the application that we're seeking out to make. But even if we, at the time when we were mired in, I've made this coating and it's still not providing me coating or cooling, excuse me, we had still developed new chemistry to chemical vapor deposit calcium carbonate and do, same thing for barium sulfate. And it's stuff like that. You don't know when that will be helpful in the future. And unconventional questions, even if you don't end up meeting a target, you still learn a lot of things on the way. And so those kinds of questions are always the best to ask.
Speaking of questions, Rory has got one. So, Rory, I'll have you go ahead and unmute and let's have you ask your question for this.
Okay. Yeah. Trisha, I have a basic question. When you started the talk, you talked about some projection going into the future. I will admit, I listen to people who have a somewhat negative view on science right now. And this is just a question. Uh, how do you measure global temperature? I mean, is it in X number of spots? Is it the same spots, or how do you do it?
So that's a great question, and I'll preface my answer with this is not my personal work or my area of
Right.
expertise. So I'm just repeating the
Yeah.
references that I did provide that I believe are good. So those numbers first were projections for the year 2091 and later, but that measurement is the ground temperature, is the maximum ground temperature per month in
Mhm.
each region. Those across different countries are measured by different sorts of organizations. For instance, in the United States, it's largely NOAA, the Oceanic Atmospheric Administration, who
Right.
and or the USGS survey that actually measures this, but they are measuring the average ground temperature. Sometimes it can be measured using radar or drones. Kind of like you're measuring a sheet pan when you're cooking. So that is what is being reported, and it is not the air temperature. It is not the temperature that the humans are going to feel, and it's a mixture of the humidity, which is easily measured by weather stations, plus that ground temperature.
When they do a reading, Is it like once a week, once a month? How's it done?
That is a limit of my knowledge, so I
Okay.
have no idea.
Well, one part of the reason I ask about this is that obviously, if you're measuring temperature at some place on dry land, uh, the temperature, however it's read, be it in the soil or in the air or whatever, is to some extent going to be contingent upon the cloud cover. And I can tell you, living here in Houston, we've gone through everything one time or another. There are some days on this date where it'll be much warmer, and other days, a year later, it'll be much cooler. And that's because the sun was shining in one and not in the other. So I'm just sort of curious. And of course, having lived through COVID, I am a little more skeptical about scientific numbers than I used to be. But yeah, okay,
So
well, I appreciate that.
so I don't know again the integration time or how long that they measured it, but for your comment specifically about cloud cover,
Yeah,
again, this number is the maximum monthly temperature. So that is basically the absolute highest number that that region reaches in 1 month. So that's assuming there's no cloud cover at one point in
yeah.
time.
Hmm.
Last question before we wind down the recording. So, Trisha, how far off are we before there are commercial products that are designed to allow people in places where there is a need for this to be able to take advantage of the kind of work you've done?
I mean, I have a startup company called Solar Yarn, and it makes the coders that are needed to basically put this specific kind of formulation down. Solar Yarn's major product is waterproofing, PFAS-free waterproofing. And we are exploring I am exploring with Solar Yarn, but also other textile manufacturers to see the best way to kind of commercialize the coating that we've made. So maybe 3 to 5 years, optimistically.
All right. Well, we will wind down the recording. We want to thank everybody who's joined us. The kind of stories that we get from around the world and how people begin to think about different kinds of challenges and the clever ways that we can find to serve communities and the kinds of ways that that happens and in different parts of the world. All very, very exciting to us. We would love your thoughts. If you're on our Rotary page at siliconvalleyrotary.com or at rotary.cool, then you might just scroll down to the bottom of the meeting that has this particular recording as its program and leave a comment in the disqus section, where we get a chance in an online and asynchronous club to share ideas with each other. Additionally, let us know you're around. There is an attendance feature form that's just a little farther down the page as well, and that allows us to better understand the reach that we have. As we always like to do, we hand it back to our speaker for the final word. So, Trisha, what would you like the person listening to this podcast, watching this video, to have clearly in mind as this winds down?
Every clothing that you wear has a finish. Usually it is just there to change the color and the hand feel. And think about how much more it could do, including keeping you cool or keeping you warm when you need it. But it could do a lot more than that. So
Wonderful. Thank you, and thank everyone for joining us. We'll see you next week.